So does anybody have any homework questions? Not yet. I know you haven't done too many problems yet. We'll get more after today. Um, but is that a no or a maybe? No. Okay. Well, you'll have other times to ask about this, but what we did last time is we derived 3 equations that are useful for constant acceleration problems. If the acceleration is changing, then you can't use these. Or not problems, 3 equations. We derive 3 equations for constant accelerations. This is important. So we're going to do a lot of problems where acceleration is constant, but that's not always the case. And the equations that we got were first, velocity is equal to v sub 0 plus at. The second one says position is equal to p sub 0 plus v sub 0 t plus 1/2 at squared. And the third one, we took those two and substituted in a way that eliminated time explicitly from it. And we got that 2a times the quantity p minus p0 is equal to v squared minus v0 squared. Where p0 and v0 are at the time equals 0 instant, and p and v are at the instant t. Okay, so there's this implied instant t, and that's what you can think of p and v as functions of the time t. What about the acceleration? When does that acceleration occur? Everything is at a single instant time except the acceleration, and that's because these are constant accelerations. So over this whole interval, the acceleration is constant. Okay, everything else needs to be represented at a single instant. Are you with me on that? And what we saw is that to use these, we had to choose a physical location that corresponded to a 0 position. We had to choose a positive direction. We had to choose an instant corresponding to time equals 0. And then we had to choose an instant for time. And that's so we're choosing an instant where that P and that V are both occurring. And I did one example last time that was a ball rolling on a ramp. But we haven't done the most important case of constant acceleration yet. So the most important case of constant acceleration is free fall. And the way I'm gonna use that term is as a synonym of projectile motion. So maybe if you think of those differently, you think of a projectile motion in one dimension. Okay, so we're just talking about things going straight up and straight down. But in one dimension, you would think of projectile motion maybe as being something being shot up, and free fall as something being dropped down. I'm going to use both of those to mean either one of those. Okay. And this brings up the first of 4 major common misconceptions that we're going to have to deal with in this class. So this class, Physics 1, Mechanics, deals pretty much all with stuff that you have intuition about. When you take Physics 2, it's going to be all electricity and magnetism, and it's a lot harder to have intuition about that stuff. You just have to kind of trust the laws and trust the calculations. In Physics 1, like, you've thrown and caught a million balls and you've seen stuff fall, and so you have intuition about everything we do. In most cases, that intuition is helpful. But there are a few cases where people's intuition tends to be wrong. And there are 4 of them that I want to bring up in this class explicitly, because when you get to these things where your intuition is wrong, you don't just have to learn the new thing, you have to kind of actively tell your brain to replace this old thing that you've lived with for however many years with the new information. Okay. So common misconception number 1. So it's often believed that gravity makes heavy, or let's say heavier objects in free fall fall faster than lighter objects. This was actually believed by, some of the most important thinkers and scientists in the world until about the 18th century, 1700s, late 1600s. And it's pretty clear why people have this intuition, because you have the experience. You don't have to get up very high to see it happen. If you take a brick in a crumpled up piece of tissue paper and drop it from 6 feet up in the air, the brick hits the ground faster. There's no denying that. And if you, the higher you go up, the more obvious it is. If you go 1 story up and drop a ping pong ball and a pinball, say, you know, the pinball hits the ground first. So there's a lot of reasons that we have this intuition. But it's not gravity that does it. The truth is, gravity accelerates all objects, no matter what their weight is, no matter what their shape is, downward at 9.81 meters per second squared. If the objects aren't affected by air resistance. You can think of air resistance this way. Any gas, and air is a gas, is just a bunch of particles, tiny particles bouncing around and they're bouncing around in empty space. And when you throw an object or drop an object in real life, this thing is bouncing into a lot of these tiny little objects, these air particles, okay, these molecules of air. And different objects are affected differently by the collisions that they're making with these air molecules. And so if you get rid of all those air molecules, like if one by one you could take those air molecules and move them out of the space that you're dealing with, what you have is a vacuum at that point, if you don't have any air molecules. And if you did that, you'd take a brick and a piece of tissue paper, and no matter how high you drop them from, they would both fall at exactly the same, they would be at the same speed at every location, at every instant. They'd each be speeding up the whole time because of this downward acceleration. Okay, well, that's mainly theoretical. So I'm going to show you a video. It's a really cool video because it's hard to make this happen. But where they go to an aerospace testing facility that's capable of creating a giant vacuum that's, you know, 30 feet high or whatever, and they suck all the air out. And when you suck pretty much all of the air molecules out of this place, they take a feather and a bowling ball and they drop them, and you see them fall exactly the same. Okay, so I'm going to show you that video. And then where we're going after that is, the next question is, okay, well, what are the things that determine how much air resistance is going to affect an object's motion? A feather is affected a lot by air resistance. That's why when you drop it, you just see it flutter gently down, okay? A bowling ball is not affected very much by air resistance. And there's a few factors that come into how much air resistance affects an object's motion. Okay, so everybody understand the idea of this common misconception? If you don't have air resistance, everything falls the same. I'm going to show that happen.
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. Space Power Facility near Cleveland, Ohio, and it is...
Okay, so here's what he's about to say. I just rewound it again. But he says there's 30 tons of air in there, okay? If you put all the air in a bag and ask someone to hold it up, it would crush them, 30 tons. And this vacuum is effective enough that they can suck out 30 tons of air and leave 2 grams left. So there are a small number of air molecules still bouncing around in there, but they make very few collisions at that point with the object that's being dropped, okay? And so the effect is that objects are unaffected by the air resistance. So is this right here before or after they suck all the air out of the... Because he's not dead, exactly. And also he hasn't exploded. So like there's a pressure inside all the cavities of your body that's equalized with atmospheric pressure, okay? And if you suddenly went to 0 air pressure, which is what would happen if you took all, like pressure comes from those molecules bouncing against the surface, okay? So if you suck all the molecules out on the outside of his body, and there's still all those molecules on the inside, and he goes in, suddenly all these, there was this equality of pressures on the inside and outside. Suddenly all these collisions on the inside with nothing fighting them from the outside win easily, and everything explodes. That's what you're feeling like when you drive over a mountain pass or something. If you increase your altitude fast, you feel your ears popping. It's because the air pressure outside is going down, and the air pressure on the inside is staying about the same. And so now the stuff on the inside is winning this battle, and it's pushing out. Yeah. Oh, yeah. Yeah, and I was going to say, the other place that you see it is, have you ever wondered why when you're on an airplane and they bring you chips or something, the bags are inflated? It's the same thing. They pressurize the cabin in an airplane, but they don't pressurize it all the way to sea level because it's expensive and people aren't active. So they pressurize it to the equivalent of about 10,000 feet of altitude. But so that means that, so these chip bags, when they're sealed at sea level, they're not inflated, and they have sea level atmospheric pressure pushing out on the inside and sea level atmospheric pressure pushing in from the outside, and those two are in equilibrium. Then you go in the plane and decrease the pressure in the cabin. There's still the same atmospheric pressure pushing out on the inside. There's less pressure pushing in, and so the inside starts to win. And if you had a bag of chips in a cabin that wasn't pressurized and you went up to 30,000 feet, the bags would pop open. That's why it used to be the case when luggage used to be stored in non-pressurized compartments in the airplane, that if you forgot to take your, say, shaving cream out of your toiletry kit, you'd get where you're going and there'd be shaving cream everywhere, because it's that same effect. Like, who's winning, the pressure outside or the pressure inside? When you dive down underwater, it's the opposite effect. High pressure outside, low pressure inside. Okay. Any questions about that before I start this? Okay.
The world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber. Aluminium.
So he concluded they weren't.
It's all the way up, isn't it?
And it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. And it's kind of got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems, and that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, the strongest material to build a vacuum chamber out of. So they built an outer concrete skin, which is part radiation shielding and part an external pressure vessel, so that this thing can take the force that's present on the outside when it's pumped out to the conditions of outer space.
Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest.
Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So in order to see the true nature of gravity, we have to remove the air.
It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
Okay, we dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCB 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
I wish they showed it full speed. They don't. That's still pretty
Exactly.
They came down exactly the same. Wow.
Look.
That's right there. Look at how they hit right there.
Exactly.
You're back on the side.
Exactly.
Okay, so, oh, and the feathers as they're coming down, there's no ripples or anything in the feathers because all that kind of stuff, what makes them ripple is the collisions with the air molecules. And so there's nothing in there, they just fall perfectly still right next to the bowling ball the whole time. Okay, so the idea of this first common misconception is when things fall at different rates, it's an air resistance thing, not a gravity thing. If all you have is gravity, you get rid of the air resistance, everything falls the same. Okay. Also, so this statement says that gravity makes things accelerate down at 9.81 meters per second squared. Okay, well, what about when you throw something up into the air? You know, is the acceleration different while it's on the way up? No. It's not. It's always accelerating down at 9.81 meters per second squared. When it's on the way up, that means the velocity is up, okay? The direction it's moving is up. But think about what it's doing. It has a upward velocity, but it's slowing down the whole time it's going up until it gets to a point where it's at 0 speed, and then it starts speeding up on the way down, okay? So let's think about those two different parts of the motion and make sense out of the fact that the acceleration is down all the time, okay? So when the thing is on the way up, it's slowing down. What direction is its velocity? Yep, velocity is up. It's slowing down. What does that say about the direction of the acceleration? Yep, to slow down, those two have to be opposite directions, okay? So we know that on the way up, the acceleration is down. Now think about when it's on the way down. Its velocity is down. It's speeding up now. So what direction does the acceleration have to be? Down, okay? So if anyone ever asks you, something in free fall, it's on the way up, what's the direction of the acceleration? It's on the way down, what's the direction of the acceleration? It's at the instant where it has 0 speed, what's its acceleration? The answer is always the same. If something's in free fall, meaning there are no other significant forces acting on it, then the acceleration is down at 9.81 meters per second squared. By the way, this is an approximation for when you're close to the surface of the Earth. So this is but it doesn't change significantly as you go up to higher altitudes or whatever. So anywhere on Earth, this is the acceleration you get from gravity. If you get farther away from the surface of the Earth, you get into orbit or whatever, the acceleration is less, but we'll talk about that later. Okay, so now the question is, we know that if you don't go through the effort of pumping the air out of a room before you drop a bowling ball and a feather, they fall very differently. It's because of air resistance. So what are the things? So air resistance clearly affects the motion of different objects differently, okay? So air resistance affects the motion of different objects differently. What are the important factors? How can you look at an object and get a sense for whether it's going to, if you dropped it, it would have roughly an acceleration down of 9.81 meters per second squared, or if gravity would have a drastic effect on its motion? Yeah, so yes, that is one, surface area. Mass is one, yes. Yep. Shape, yep. So if it's very aerodynamic, and there's one more important one. So think about, yeah. Density is really connected to the mass, kind of. But think about if you, drop a baseball, yeah, let's say, imagine dropping or even a beach ball, let's say a beach ball, and you drop it from here to the table, okay, and you measured its acceleration, you would get about 9.81 meters per second squared. Air resistance wouldn't affect it very much. If you went up to 6 feet, it wouldn't be an acceleration of 9.81 meters per second squared. So what's the difference between those two? The speed, yep, speed is the last one. And actually, speed is the one that has the biggest effect. We'll see that in a lab coming up. Okay, so let me just go through the ones you all came up with, all of them. So the first one is the object's mass. So everything else being equal, an object's motion is affected more as the mass decreases. And one way you can think about this is like a ping pong ball and a pinball are, the same shape, somewhere around the same size. The only real difference between them is the mass. So if you drop the two of them, the pinball, if you drop them really close to the table, say, they'd hit the ground at the same time. But if you go up 10 feet or something, the pinball is going to hit the ground first. That's because everything else is equal, but the masses are different. The second thing is the object's shape. If everything else is equal, a more aerodynamic shape is going to have less air resistance. So I'm going to keep doing it by what makes the effective air resistance greater. So the object's motion is affected more as the shape is made less aerodynamic. The third one is the object's area perpendicular to the direction of motion. Somebody said surface area. You can sort of roughly think of that as surface area, but if you have a really long object, okay, that has a big surface area. But if you're dropping it like stick down, the large area connected to its long length doesn't affect it. All that matters is the area that's perpendicular to the direction of motion. Okay, so the object's area perpendicular to the motion. I'm going to abbreviate this, all else equal. An object's motion is affected more as that area increases. And then the last one is speed. So object speed. So again, all else equal, the object's motion is affected more as speed increases. So like think about the difference in shape between like a wagon and a Ferrari or something. Okay, like a kid's wagon and a Ferrari. They're both designed to roll and move. When a kid's pulling a wagon, is there a lot of air resistance acting on it? No, even though it's a super boxy shape, you wouldn't describe it as aerodynamic in any way. But it's going so slowly that there's no significant air resistance. But if you put a Ferrari engine in a flexible, what are those called? The Flyer, those red wagons, there'd be a huge amount of air resistance because as the speed increases, the effect of the air resistance goes up. And that's why cars that go 200 miles an hour are made with very, very streamlined shapes. Things that are designed to go more slowly, they don't care about that. Any of you guys ever watch bike racing? It used to be really popular before Lance Armstrong was found to use drugs and stuff. Like everyone's like, oh yeah, Tour de France. Now everyone's like, they race bicycles. But anyways, there's like in the Tour de France, there are like one of the small number of chances that someone, so they have 21 races, long races. Most of those races, there's not much of a chance for someone to gain time on anyone else. One of the big places where you can gain time is the time trials, where they stagger people and they go out on their own, because then you can't tuck in behind someone, and the air resistance has the tendency to bring the field close together. But if everybody has to fight through the air resistance on their own, then there's a chance for big differences in time. And they do two different kinds of time trials. Most of them are flat, okay? Some of them, though, go through the Alps or the Pyrenees, go up these gigantic mountains. And when they're doing the flat time trials, they look like aliens. They're in almost space suits. Everything's rubberized. Their bikes are designed to have them in this position the whole time. Every concession is made to make them as aerodynamic as possible. Okay? When they're doing the time trials where they're going up the mountain, it's a totally different thing. They have regular bike jerseys on, unzipped to stay cool, and they're wearing regular helmets, and they don't even have the time trial bars. They don't seem to care about air resistance in the least. So what's the difference between those two? The difference is those guys, when they're moving along the flat, can ride at close to 40 miles an hour. When they're going up the mountains, they're going 10 to 15 miles an hour. And that difference in speed is enough to take air resistance to being almost the entire game to making air resistance almost negligible. All right, so let's do some problems. Well, one problem at least. Okay, so let's say that you're on top of a bridge and you want to know the height. And so what you do is you drop, let's say, an object for now. Off the bridge and time how long it takes to hit the water. Okay, so let's say that you time it and it takes 0.80 seconds. How high is the bridge? Okay, well, I have two questions before we do this calculation. The first one is, what kind of object are you going to drop? So you don't want it to be a feather or a ping pong ball, because we're going to make the assumption that air resistance doesn't have a significant effect on this motion. So you want it to be a rock or something. And if it is a rock, you want to make sure no boats are going under the bridge.
They won't catch you.
Yeah. So you want it to be something that, as much as you can make it, decreases those 4 factors that determine air resistance effect. Okay. Yeah. Yeah, usually there's a whole collection of things to choose from at the top of any bridge. And what if you timed it and the time was 16 seconds? What would that tell you about your estimate of the time of the distance? You'd be a little skeptical, because by the time something's fallen for 16 seconds, it has, if there was no air resistance, it would build up so much speed that it would be going super fast. In other words, it has time to build up enough speed for air resistance to affect it quite a bit, almost no matter what it is. Okay. But for smaller distances like this, it's probably a pretty good estimate. Okay. Okay, so what are we gonna, so for this calculation, there's the bridge, here's the river. Here's you. And we have to choose those 4 things. We have to choose a 0 position in a positive direction. For free fall problems, I pretty much always choose my 0 position to be the lowest point in the motion. You don't have to, it's arbitrary. And I always choose my positive direction to be up, so I'm going to call that positive. And then I'm going to say my time equals 0 is the instant that it's dropped. My time t is going to be when the object hits the water. And does anyone remember what are the criteria for how you choose time equals 0 and time t? Those are places where you're given information and or you're looking for information. Okay, so we know some things about what's happening when it's dropped. So what do we know about the object at the instant that it's dropped? Yes, exactly. We know that its velocity is 0. And we know a bunch of stuff when it hits the water. Well, we know the elapsed time. Maybe that's all we know. But we're also looking for the position when it hits the water. Okay, so here are all our options for variables. So T, A, P sub 0, P, V sub 0, V. Do we know the value of T?
0.
Yeah, so time equals 0 is always 0. So the only one we care about is the 0.8. Okay, so this one is 0.8 seconds. Do we know the acceleration?
Yep, 9.81 meters per second squared.
That's right, and that's its magnitude. And then you have to think about how the direction relates to our positive direction. So it's negative in this case. Do we know the position when time is equal to 0? It's no, it's not 0. That's what we're trying to find. So this is what we want. Okay, because the 0 is at the water. So do we know P? Yeah, that's the one in this case that is 0. So it hits the 0 position as the stopwatch hits 0.8 seconds. Do we know the velocity at time equals 0? That's 0. And do we know the velocity at time t? No, we don't know that. One thing that a lot of times people think is like, oh, well, you hit the water and it stops the thing. But these equations only work during the free fall part. As soon as the object touches the water, these equations don't work anymore. So what we're really talking about here is what's the velocity at like the instant before it makes contact with the water. So we don't know that. And so now, is there an equation that works to let us calculate P0 given these other ones? The second one, that's right. So P is equal to P0 plus V0 T plus 1/2 A T squared. So 0 is equal to P0 plus 0 times 0.8 plus 1/2 times negative 9.81 times 0.8 squared. Solve for P0 and you get .1, call it 3.14. What's the significance of that being pi? There's no significance. That's a random coincidence. Okay, does it make sense that that's positive? Yeah, because we know that it's dropped from somewhere in the positive direction of our 0. Okay, let me say two more things. So 2 useful facts. This will come up. That's not a word. 2 useful facts. The first one is if an object is launched up, then it reaches its highest point when the velocity is equal to 0. Okay, so if something is launched up into the air, it starts out with a upward velocity, slows down until it has 0 velocity, that's the highest point, and then it starts to have a downward velocity after that. And the second fact is if an object is dropped, like it was in this case, its velocity at the instant of release is the velocity of whatever it's dropped from. So in this problem, the object was dropped from a bridge. A good quality bridge has 0 velocity. That's what you're looking for in a bridge. And so that means that at the instant the thing was released, the object has 0 velocity too. If instead you drop a ball as you're going up in an elevator, at the instant you release the object, it has the velocity of the elevator. And then it'll start its acceleration downward at 9.81. Any questions? Okay, I'll put up some problems for you to work on. And then tomorrow we'll do some problems together.